Session outline. What we're going to do today, or by the end of this session, you should be able to calculate current and voltage in series circuits, in parallel circuits, and in combination circuits. Alright, so we looked at the total resistance of series, parallel and combinations last week. Now we're going to add some voltage to those and calculate currents and volt drops across components. Okay? So, first of all, symbol, common symbol for a voltage source, in this case a DC voltage source, is a circle, as so. Quite often sources are given the designation E for EMF, okay, but sometimes voltage as well, so you have to get used to them being different. This symbol here, one straight line and dashed lines underneath, is a symbol for DC, okay, and this arrow here indicates, well, the head of the arrow is the positive terminal in terms of convention for polarity. Okay, so what we're saying is, from that source, if there was current going to flow from it, it would flow by convention in that direction, with the arrow on the source. Alright? So the arrow points towards the positive terminal and the direction of current. If we have a resistor in a circuit, here R1, we designate the potential difference across it, or the volt drop across that resistor. Remember, volts is across, current goes through. Always remember that, right? We have an arrow that points towards the most positive end of that component, okay, and against the direction of current through it. Okay, and as we do this circuit analysis techniques that we're going to do, putting your current arrows and your volt drop arrows on in the right direction is really important for solving the problem correctly. So you need to get that down now. Okay, so the arrow or resistor shows a volt drop across it. Please don't do that, because that doesn't give the polarity. We want an arrow on one end towards the more positive end. Alright, and I'll clarify that a little bit further when we look at an actual circuit. The arrow points against the direction of current. Okay, don't know why I've written that twice there. Bit of a typo. Anyway, that's fine. So, if we look at a series circuit, commonly known as a voltage divider. Okay, so we've got a source E, arrow pointing that way, so that end is the positive end of the source, that end the negative. We'd expect current to travel away from the positive all the way around the circuit and back here. Should also be aware that the same current flows there. In a series circuit, there is only one current. There are no leaks. Every bit of current that leaves this positive terminal comes back in the negative terminal as well. Yeah. In a series circuit, there is only one current. Okay. Then what we can say about this circuit is we've got two volt drops across components. This end of this component is closer to the positive terminal than this end. So that end is more positive than that end. Alright, and therefore our volt drop arrow points that way. Notice it's against the flow of current. And the same with this one. Although that terminal is considered more negative than that one, this one's at the same potential and it's closer to that positive terminal than this end is. So that's negative. Arrow goes that way, current is travelling through that component in that direction. All okay with that? Yeah? Now, calculation-wise so far, we already know that we can calculate some of these values if we wanted to. We could calculate using Ohm's law. So this is Ohm's law. We know that the current flowing in the circuit is the voltage E, the total voltage divided by the total resistance. So if we knew the values for them, we calculate that. We know that we can calculate the total resistance from that formula, add them together. Okay, so we can replace RT in this Ohm's law with R1 plus R2 in Ohm's law if we wanted to. We want to understand that. Yeah. Also, we could calculate individual volt drops, these two, V1 and V2. We isolate just that component. The total current flows through it because it's a series circuit. We use the individual resistance to calculate just the volt drop across that one resistor. We isolate this component and we use the same current because it's the same current flowing through it, but we use the value of R2 to calculate the volt drop across there. And what you'll see in a minute, and we'll also clarify and solidify with Kirchhoff's voltage law probably next week, maybe the week after half term, is that these two voltages dropped here will always add up to the same as that one. It divides that supply voltage according to the ratios of the resistors, as you'll see in a minute when we do some calculations. And hence it's called the voltage divider. So a series circuit is a voltage divider. All happy with that so far? Yep. So, resistors of 20 ohms, 75 and 120 connected in series. Across the supply of 100 volts. We'll call that E. We'll call this R1, R2 and R3. Yeah, calculate the current flowing. So we're going to apply pi and volt drop across each resistor. Which way are my arrows going to point on the top line there across each of those resistors? To the left. Yeah. Okay. Call that V1, 2 and V3. So we're going to calculate those values in blue. Yeah. Where do I start? Yeah. So we can go RT, R1 plus R2 plus R3 20 plus 75 plus 120 equals 215 ohms. Yeah. Now what can we do? Pi. What can we do now? Now we've calculated the total resistance. Ohm's law. What can we do now with Ohm's law? Now we know RT. What can we find now? So we can find, using Ohm's law, I is E over the total resistance. Yeah? So that's the 100 volts over the 215 equals 0.465 amps. Yeah? Now what can we do? We can find the individual resistor voltages, because V1 is I times R1, 0.465 times 20. V2 is I times R2, 75, and V3 please give me some answers. Sorry? 9.3 volts. 30. There's some rounding in there, isn't there? Okay. I'll check to add all them up. Approximately equal to the 100 volts of the supply. Yep. So I would imagine the current was rounded slightly. Yep. So as a worthwhile check when calculating individual circuit voltages, that you add them all up and make sure they add up to the supply voltage in a circuit that's all series. Okay, we can change those values of resistor to what we like. The current would change, the values of each voltage across would change, but the fact they all added up to 100 would never change. Kirchhoff's law for voltage is always obeyed at all times in any circuit. And no matter how far you go into electricity, how complicated you get with it, these laws still apply. Yep. They still apply in AC circuits. The maths gets a bit more complicated, but these laws still apply. Okay? Everyone happy with that? But these 3 volt drops here, when you've calculated them, should all add up to that 100 volts that you applied in the first place. Yeah. So if you knew these 3 voltages, you could add them together to find out what the supply voltage was. So that's about finding a way to tackle a particular problem. Now, there's a particular thing that you can do with a 2 resistor potential divider. We've already discussed that the total resistance of this is R1 plus R2, and we can write that, instead of RT in Ohm's law, we can write in that the current is the voltage divided by the two resistors added together. Yeah. In the case of V1, the volt drop across the resistor R1, we could calculate that from I times R1. If we substitute this equation into that equation for I, we get that. We've got an expression now for the volt drop across one of the resistors without involving the current. So if we know the two resistor values and the supply voltage, we can find V1 without finding the current first. Yeah. And equally, for V2, same formula except for that's R2 instead of R1. Alright? Either way, if you're given a problem, unless you're specifically asked to use the voltage divider rule, if you're more comfortable doing the individual calculations and you lay it out properly in an assignment and say what you're doing, no problem with either way. Okay? There are some problems perhaps later on in your learning where you'll need to use the voltage divider rule because there isn't a way to find the current for one reason or another. Okay? But it's the rule is saying that the voltage divides up in proportion to the values of the resistor. And if you think about the principles, the biggest voltage is going to drop across the biggest resistance. Yeah. Smaller resistance, smaller volt drop. Bigger resistance, more volt drop. Right? Any questions so far on the series circuit and voltage divider? Oh, hang on. Right, voltage divider. Have a go at that problem. Voltage divider is to give an output voltage V2. So they want this voltage to equal 18 volts. From an input E, 45 volts. Yeah. Given that R2 is 50 ohms, calculate the required resistance for R1. Notice the question doesn't say calculate the current. But using the voltage divider rule and rearranging it, we can do that. So what's the formula for V1 in the voltage divider rule? Yep. Now you can test your skills at rearranging formulae to rearrange that for R1. How are we going to find out what V1 is? Yeah, that's the E minus V2. Because if those two add up to make 45, then that minus that must equal V1. Yeah. So you got the V, you get V1 from that. Now you need to rearrange that for R1. are we going to rearrange this formula for, so we got R1 equals something. We can't do just R1. But what did I say about a line like that? What does it imply? Brackets. So we can multiply both sides by R1 plus R2. Now what? And that was? Remember, we want R1 on its own. Yeah, divide. And that's not divide by R1, R2, that's multiply by R1. Divide by E, we get R1 is equal to V1 times R1 plus R2 over. Now we can put our numbers in. That's 18. You do, don't you? Yeah. Mike, not looking at it. Silly. It's getting late in the day for maths, isn't it? How are we going to get those two R1s together then? What do you reckon? What? Do what we did. What happens? Let's have a look. What happens if we multiply these brackets out? Now, what can we do? Could do, but I ain't got to teach you anything, is it? Come on. Keep working. You can't take away R1 from both sides, can you? Need to get the two R1s together. If we subtract V1R2 from both sides, what do we get then? Now, how can we get this R1 over to that side? But we can't divide it because it's connected to this by subtraction. There's a plus in front of that, remember? V1 R1 minus E R1. Hang on. Now what can I do with R1? Factorize it. Yeah? Remember what we had this morning with that problem? We had to get the two variables that were same together and look for a way to factorize them. So they only got one of them. R1 on its own now. Not overly comfortable with this negative sign here, but we'll leave it like that. Now what can we do? I'll write down what each stage is in a minute. We don't want to multiply these brackets out. We want R1 on its own. So if we divide by V1 minus E. Yeah. I'll write down what each stage is in a minute. Numbers. What is V1? 18. 27. R2. V1. 27. Minus 45. I'll go through it all again in a minute, what's done at each stage. Everyone agree with that? And that's not volts, is it? Ohms. Yeah. Okay. So that resistor, 75 ohms. Yeah. So the stages in this rearrangement were multiplied by R1 plus R2 in brackets to get that. There it is. Okay. Multiply 8 brackets. So V1 times R1, V1 times R2, equal to E1R1. Yeah? Subtract this V1R2 from both sides. So we end up with this. There's the V1R2 subtracted from that side. Factorise R1. So that ain't what we did next, that's the next step. This one is subtract E1R1. Taking that away. There it is, subtracted. Then factorise R1. There's the factorised term. Divide by V1 minus E. Get that, there's the V1 minus E. And then we're ready for numbers in, because we got R1 equals something. Here's a particularly tricky one, I accept that. Okay. Yep. Hurry up. What is what? Yeah, there is a yeah, probably me just touch the board accent. Not me. Where can you see it? Here. We will get to circuits where there's E1 and E2, so red and right. Current divider. So if we connect two or more resistors in all parallel, okay, what we've got is we've got a source voltage here, suggesting that's the positive, that's the negative end of that terminal, and voltages across here, V1 and V2, must be the same. Yeah? Because they're connected in parallel. All that wire is considered to be at the same potential, all that wire is at the same potential. There's just one volt drop in that circuit, and that will be equal to the supply voltage. If it's all parallel, then every component gets the supply voltage across it. So where there was one current in the all series circuit, there's only one voltage in the all parallel circuit. Okay. But when we get to this connection here, quite commonly known, and that connection known as nodes or connection points, this current IT splits into two separate currents, I1 through the resistor R1 and I2 through the resistor R2. They both come back together here to make up IT again, because everything that leaves this terminal comes back to that terminal by one route or another. Yeah? And the current will divide in a ratio of the resistors. However, more current will go through the smaller resistor, less current through the bigger resistor. That kind of makes sense if you think about it electrically. The more resistance there is, the less current is going to flow. Yeah. So yes, it is a ratio thing, but the ratio is the other way round. The most current goes through the smallest. Whereas the volt drop, the biggest volt drop was across the biggest. All right. So what, calculation-wise, what we can do is we can calculate, we can say that the total current is these two currents added together, and we'll formalize that next couple of weeks with Kirchhoff's current law, okay? And we can calculate each of those currents from the supply voltage, because it's all parallel, divided by firstly the resistor I1 to get the current R1 to get the current I1, and the resistor R2 to get the current I2. Yeah. Current divider. All happy with that? So again, as Ohm's law, total resistance, they're the only calculations we've got involved with at this stage. All right. Example problem. 66 ohm, a 33, and a 56. See, doing it by ratios is all right when you've got easy numbers like 2, 3, and 4. But when you start getting trickier numbers, the ratio way becomes more tricky. Ohms. All of that connected in parallel to a 24 volt supply. Calculate the total effective resistance. So we want RT. That's a question mark. The supply current. So we want IT. There's a question mark. And the current in each branch. So we want, mark them in a different colour, I1, I2, and I3. Right. So I, how are we going to calculate the total resistance? I want RT. What's the formula for RT, parallel circuit? If you do it that way, it must be 1 over RT. Or we can do this formula, RT is equal to brackets R1 minus 1, R2 minus 1, R3 minus 1, all to the power of minus 1. Yep. So that is brackets 66 minus 1 plus 33 minus 1 plus 56 minus 1. Presumably someone pushes the button somewhere. Does that look right from the rule of thumb that we know? What's the rule of thumb? Parallel resistance. Total is always going to be less than the lowest. So we're on track in terms of that. We still could be wrong, but we're in the right area because it's smaller than 33, which is the smallest one. Yeah. IT, how are we going to calculate that? Current is through. Yeah, I know you can calculate the currents now, but let's do it in the order the question says. Yeah. $15.8. All right. So IT is equal to, by Ohm's law, the supply voltage is 24. One point something. $1.52 amps. Yeah. IT. How do we calculate I1? E over R1, 24 over 66, isn't it, that one? .36 amps. I2, E over R2, 24 over 33. Point something. .72 amps. And I3 is 24 over 56. 0. What? 43 will do. Keep them to the same number of significant figures. Yeah. Check is, add all them up. What do we get? Which is approximately equal to the 1.52 we calculated using the total resistance earlier. Yeah? So that and that version of IT matches each other. So it's a useful check either way. Yeah? All happy? Yeah? Shout if you're not. You say yes, I'm going to move on. Right, combination circuits. Here, we've got a combination of both parallel and series. Yeah, so we got E is 30 volts. current's going in that direction, so that must be the arrow. We've got R1, 10 ohms, R2, 30 ohms, R3, 50, and R4, 15 ohms. Okay, and the question says find all unknown voltages and currents. So we've got at the moment V1 across the resistor R1. Arrow's going that way because the current's going the opposite direction. We've got V2 across the resistor R2. What's the value of V3 going to be in terms of other values? Exactly the same as V2. Those two are in parallel. They've got the same volt drop again across them. Yeah. We've got V4 across R4, and we've got a current I2 going through R2 and a current I3 going through R3. All those unknown things plus the total resistance we want to find. Yeah. Find all that. So let's start with R2. Can we write an expression for the whole thing in go? R1. How can we write an expression for the two resistors in parallel? We can use that product over sum rule, can't we? That's what you're saying, isn't it, Toby? Yeah. So it's R2 times R3 product over R2 plus R3 sum. Yeah. And then add on the value of R4 in the end. If you can do it that way, right? Listen, guys, if you can do it that way, you're not going to calculate the value of that and round it and then add to the other two. You're going to get one answer that you can round at the end. All right? If that gets too complicated, that's impossible. But for a circuit like that, it's reasonably easy using that product over sum rule to write one expression for the whole thing. And now we can put the values in. So R1 is 10 plus R2 30 times R3 50 over 80 plus R4, which is 15. And that equals. See what other people get, see if they agree with you. Okay. Yeah, everyone got that? You've done them separately. So sometimes it don't matter, but when you get odd numbers involved, you're only doing one lot around, and that's my point. And you're just doing one calculation. Either way, unless you're specifically asked to do it a particular way, I don't care as long as it's about whether you get the right answer or not. Right? So we'll just make a note of that on here. RT is 43.75 ohms. What value can we find now? Yeah, we can find IT. Because IT is equal to which voltage? Yeah, E over RT. Yeah. Yeah, 0.69 amps. So again, I'm going to write that on the drawing. The value we calculated, 0.69 amps. Yeah. So, what two other values can we now find? Now we know that current. Not quite, not yet. Because to find I2, we need, remember, to use Ohm's law, we need to know 2 of the 3 quantities to find the third. All we know at the moment about that route is R2, and all we know about that is R3 value at the moment. You can find V1, yeah, because we know 10 ohms, and we now know the current flowing through it is 0.69 amps, we can find the volt drop V1 across that resistor. So we can say V1 is equal to IT times, what was the value of the resistor? 10, wasn't it? Equals 0.69 times 10 equals 6.9 volts. Yep. V4, if we know the current through it, IT times R4, 0.69 times 15, 10 point what? So we'll do 0.4, we'll round it to 3 significant figures, we'll keep in the same kind of, we're not going to use 4 significant figures there unless elsewhere, alright? So that's volts. Hang on. Yeah, so let's put the 6.9 and the 10.4 on. So now what can we find? Exactly. This, what you're saying is, you can find V2 by taking these 2 voltages away from that, because we know them 3 add up to 30. So if we take those 2 away from 30, we'll find V2. Well, V3 and V2 are the same, yeah? So what we could say to clarify that we know that is V2 is equal to V3, and it's equal to E minus V1 minus V4. 30 minus 6.9 minus 10.4 equals. Yeah. All right. Okay with that? Yeah. So we got 12.75 across here. You're all happy that that voltage is the same as that one, because they're both in parallel with each other, no other involvement. Yeah. So now what can we find? Final 2 things. I2 and I3. I2 is equal to YE. Careful. You've got to isolate. This is one of the most listen, guys, and I want you all to listen carefully now. One of the most common mistakes calculating individual currents in a parallel part of an overall network involving parallel and series, so a combination circuit, is to try and calculate that current using the total voltage. No, you have to isolate that resistor and use the voltage across it and the value of that resistor only to calculate that current. And isolate those 2 to calculate the current I3. You can't use this 30 volts. And that's a really, really common mistake. Alright? So it's for the V2, it's going to be for the I2, it's going to be V2 over 30 over R2. And this is going to be V3, which is the same for R3. I2 is V2 over R2. That's 12.75 over, what's R2? 30 equals, and I3 is V3 over R3, 12.75 over 50, innit? What are those two currents coming? 0.425 amps, 0.254 amps. Check. Add them up. 0. And that's approximately equal to what we calculated for the total current in the first place. 0.6. Yeah. So we've done several bits of rounding and fiddling about there, so you wouldn't expect them to be exactly the same, but they're in the same. If you read all your cut through and didn't round anything, it would be exactly the same. All right. Sorry? Yeah. But I've given you the extra information that was missing, so I gave you 2 amps there. Therefore, these two currents we know must add up to that total. So therefore, I3 must be 3 amps. Yep. Given that, we can use this 2 amps and that 15 ohms to calculate that volt drop across there. That's 30 volts. We know that because those two are in parallel, that's 30 volts. We can use the 5 amps and the 5 ohms to get 25 volts across there. And we can use the 5 amps and the 18 ohms to get 90 volts across there. Everyone agree? Yeah? And if that was an assignment question, I'd expect you to lay that all out how we've been doing it. But the numbers there are pretty easy, so that's new. So we can now use that 30 volts to find out, and this 3 amps to find out the value of the resistor R3. R3 is equal to 30 over 3, 10 ohms. Yeah. So it's a similar circuit, but you are given different information. The point I want to make is finding this E. We know we add these voltages up, but we don't add the 30 on twice. It's around one loop. So the total voltage is 25 plus 30 is 55, plus 90 is 145 volts. Yeah.